Welcome to our help video, and this video will begin on page 6 of the test. This is page 6, and we pick up with question 33 dealing with our diagram right here. Right in this diagram, they told us that there's 16 protons and 18 neutrons in the nucleus. What do we get from that? Well, from 16 protons, we should be able to tell who this is. Remember, it's the number of protons that identifies the atom. So who's number 16? If we take a look on our periodic table, we'll see number 16 is sulfur. So the element in the diagram is sulfur. We know that right now. We also know its mass number. Mass number is the total particles in the nucleus. This thing has 16 plus 18. That's 34 nucleons, or 34 particles in the nucleus. Its mass number is 34. Mass number is telling you how many particles are in the nucleus. Let's take a look at the electrons orbiting the nucleus, which are these blue dots in this diagram. We have 2 on the first level closest to the nucleus. That's filled with 2. Then the next level has 8. 2 and 8, that's 10 electrons. The next level is full. The valence level, or the third level, the outermost level in this case, also has 8. 2 and 8 is 10, plus another 8. There's 18 negative electrons. Take a look at the number of positive protons in the nucleus. There's 16. What can we tell from that? Well, there's 2 more negatives, 2 more electrons than there are positives, or protons. So we already can tell from this diagram that this thing is 2 minus, it's sulfur, its atomic number 16, its mass number is 34. Let's hit the question. The atom in the diagram is an anion with 2 minus. Absolutely. 18 negatives, 16 positives. There's 2 more negatives than positives. It's 2 minus. The hyphen notation would be sulfur, hyphen 16. No. We know when you use hyphen notation, we are assuming you have a periodic table. They would not tell us the atomic number. They would not tell us that there's 16 protons in hyphen notation. Why? All sulfurs have a 16. 16 for atomic number. What do they tell us in hyphen notation? Well, not every sulfur is exactly the same. Every sulfur atom must have 16 protons, but every sulfur can have different numbers of neutrons. In other words, different isotopes. Hyphen notation is the element's name or symbol, hyphen mass number, and we already talked about the fact that the hyphen notation here should have a mass number of 34. There's 34 nucleons. The atom represented in the diagram has satisfied the octet rule. The octet rule says 8 electrons, regardless. Every level after the first needs to have 8 on it in order to be full. It can have more than 8, but it needs to have 8. 8 in the outermost level. When I say more than that, that was a little confusing. The outer level should have 8. Some of the levels, though, can hold more than 8, but the outer level, it needs 8 to be stable. So it satisfied the octet rule. Again, this is sulfur. It's 2 minus. What can we tell from the fact that it's sulfur 2 minus? It means that sulfur started with 16 electrons and gained 2 more to now have a total of 18. It's going to be stable like argon is. It's going to be stable. Does sulfur like to become the sulfide ion and be 2 minus? If we come down here and look, absolutely. Sulfur does become 2 minus. It becomes the sulfide ion. Sulfur is in family 6. It loves to get 2 minus because when you take 6 and add 2 to it, you end up with 8. What about the next one? The diagram has 18 valence electrons, letter D. Yes, we've already talked about that. There would be 18, just like argon. The symbol, nuclear symbol, would be this one below. Well, we know it's 2 minus, so that we need to put the charge on it in the nuclear symbol. When it's an anion or a cation, regardless, you put the charge in there. We already talked about the atomic number. It goes in the lower left-hand corner. That's the number of protons. So there's our 16 from the diagram. 16 protons should be in the lower left. The upper right as a superscript should tell how many total things are in the nucleus. 16 plus 18 is 34. That is the correct nuclear symbol. Now we go on to the problems. Again, when we do the problems for this class, above the expression, and it was already put on there for you, but above the expression, you put little brackets saying which isotope is contributing and how much it's contributing. You identify the isotope or the information that you're filling inside. You show all the work, and you don't round the numbers until the end of the problem. So on this problem, they've given us 4 isotopes of strontium, 84, 86, 87, and 88. Here's the nuclear symbols. Notice the nuclear symbols all have to have the same mass, or same. Where they are different is in mass numbers. This one's mass number is 84, this one's 86, this one's 87, this one's 88. So they differ in numbers of neutrons. Here's the mass numbers of the different isotopes. Notice this is strontium 84, but the mass is less than 84. This is strontium 86. The mass is less than 86. 87 is less than 80. 86.9 is less than 87. 88, 87.9 is less. Why are the masses of the actual isotope less than the mass number? It's because some of the mass from the protons and neutrons ended up contributing towards the energy, the binding energy, holding the nucleus together. That's called mass defect. They can also be slightly more than the mass number, because remember, protons and neutrons are actually a little bit more than 1. So when you add up the mass of the protons and neutrons, it's more than the actual number of protons and neutrons because the mass is a little bit more than 1. Here's our abundances for each of those to the left or to the right, far right side of the column. Now when we do this, we put these back. We remove them from percent form. We put them back into decimal. When you put something into a percent, you multiply 100 by 100. So to pull it out, we divide each of these by 100, which has the same effect of moving the decimal to the left. So the first isotope we're going to be looking at is strontium 84. Notice right here in the brackets, we're trying to calculate the average atomic mass of strontium, and the first contributor is strontium 84. Slide this 2 to the left, making it 0.0056. There's our 0.0056. And here's our mass, 83.9134, and we plug it in there. Our next one, slide the decimal 2 to the left, making it 0.0986. That goes here. We're looking at strontium 86's contribution. Its mass is 85.9093. That goes there. The next contributing isotope is strontium 87. It's 7%. Remove that from percent by dividing by 100, sliding the decimal 2 to the left. That's 0.700. Its mass contribution is 86.9089. And our final one, our most abundant one, is 82.58. Divide it by 100 to put it back in decimal form, sliding it 2 to the left. That's 0.8258, and it's contributing 87.9056 mass. Now you can just put this into your calculator using parentheses. Parentheses, that number times that number, parentheses, plus, parentheses, that number times that number, parentheses, plus, parentheses, that number times that number, parentheses, plus, parentheses, that number times that number, parentheses, equals 87.62 when we round it. Here I've shown you what each of these would come out to. So if you do this independently, it should be that. This independently should be that. And if you add these numbers together, we would get 87.62. That's what this additional new periodic table that we put on there. This one goes out a few more decimal places. If we look at strontium, it is right down here, 87.62. So we're happy to realize that we've done this calculation correctly. And we move on to our final problem, our final question on the test. Problem number 2. This time, they're giving us the atomic mass of boron as 10.811. Where did they get that? On this table, 10.811. Notice this table right here, the one we normally use, just goes to 10.81. These tend to round to the hundredths place for most of our elements. That is because for most of our calculations, that's all we need. But when we're dealing with atomic mass, this is a nice table to do. This is a nice table to use for atomic mass. All right, so this time they've given us the average atomic mass of boron. And they gave us the information we need for boron 11. Boron 11, its mass is 11.009305, and 80.1% of all boron atoms are boron 11. They told us that 19.9% of all boron atoms are boron 10, but they didn't give us the mass for boron 10. So when we go to plug our numbers in for boron 10, we can use the fact that it's 19.9%, but in these things we don't want them in percent form, we want them in the decimal form. So if we divide 19.9 by 100, that's the same as sliding the decimal 2 to the left, we get 0.199. And we don't know what boron 10's mass is. That's what we're trying to find. Now you're like, well, do we need to put the 5 in nuclear symbol format? No, in this equation you don't need the nuclear symbol format. 10 as a superscript with a B after it is a shorthand way of writing that, in case you're confused by what that is. This is not intended to be the nuclear symbol format. It's just to be a shorter way of writing B10. We do know boron 11's mass. It's 11.009305. We plug that in. 80.1% of the atoms are boron 11. But we've got to pull that out of decimal form by dividing by 100, which has the effect of sliding it 2 to the left, 0.801. So now what are we doing? We are merely going to solve this equation. I plugged in the 10.811 for the average atomic mass, which they told us right here. So when we do all this calculations inside this parentheses, and add them together, it should be 10.811. Now, how do we go about solving for boron 10, our unknown? Some people like to put an X, a Y, or a Z in there. That's fine too. But those letters would just be representing boron 10. So first thing we do is resolve what's in the parentheses here. We take 0.801 times 11.009305, and we get 818.453305. Again, don't round in the middle of the problem. It can throw your answers off. So we now know 10.81 equals 0.199 times boron 10 plus this number. We want to isolate our B10, our boron 10. So what do? Well, I have plus 818.453305. How do I get rid of it off this side in my attempt to isolate this variable? Answer is subtract it from both sides. So I subtract 818.453305 from this side. If I do it from this side, I subtract it from this side. This minus this will cancel that out, leaving me with just this, what's inside the parentheses on that side. On this side, I can resolve 10.811 minus 8.818.453305. You get 1.99. 254.6695. Now I'm ready for the next step. My equation looks like this. I'm trying to isolate the boron 10. If I'm multiplying 0.199 times that, I can divide 0.199 from that side. If I do it from the right side, I do it from the left side as well. 0.199 times boron 10 divided by 0.199. The 199's cancel out, leaving me with the boron 10, or factor out, leaving me with boron 10. If I take 1.99, 254.6695, and divide it by 0.199, I get 10.01. If you have more numbers than that, I'm just rounding to 10.01 right here. That's what I've gotten. If you get more numbers than that, that's okay. Why did I round to 4? That's a good question. I probably could have or should have just rounded to 3 places, because these percents are just given with 3 numbers. So if you just put 10.0, that actually is rounded a little more correctly using the rules of significant digits. But your answer again, around 10.01 AMUs for the mass of boron 10. Hopefully these videos are final video on the 3B13 test. If you have any questions that weren't covered in the video or explained clearly in the video, don't hesitate to ask. Thanks for watching.